Hello. In this lecture, we are going to put together a lot of ideas that we have learned till now and understand about a CW output laser. The main purpose of putting it all together is to figure out, do we get a single mode oscillation from a laser, or we need to do something extra to make sure that we obtain the single mode oscillation. So let's just briefly look at the concepts that I require, which you already know of. We talked about longitudinal modes, and this is what I mean by picking up a specific single mode oscillation. By that I mean picking up a specific longitudinal mode for oscillation. You remember that there are multiple modes which are possible. C by 2L was the separation between modes, but of course we looked at the notions of frequency pulling that led to a slight decrease in the separation between the modes. But then there are multiple modes available, and how does one choose a single mode out of these? The second issue that we are not worried about at the moment is the transverse modes, but they of course play an important role. But at the moment when I'm talking about single mode oscillation, I'm focusing myself to the discussion of longitudinal modes. We have not talked about polarization. We simply ignored it until now, but actually there is a way of uh, making sure that we get polarized output. So we need to actively choose the polarization in order to obtain polarized output from a laser. And I will just indicate one method, which is the use of the Brewster window to do the selection in polarization. Then we have talked about gain. We have talked about the small signal gain. When you have very little radiation within the cavity, you talk about small signal gain, but then the gain gets saturated, and you have the notions of gain threshold, which is simply the measure of loss in the system. And then when I want a CW output, we brought in the idea of gain clamping. Let us see what is the consequence of gain clamping in a homogeneous medium. Then, of course, we need to worry about the broadening mechanisms. And you will see that when I have a homogeneously broadened mechanism in comparison to inhomogeneous mechanism, the effects on the mode selection are very different. And then, of course, the notions of saturation, which I already mentioned. So all these ideas we are going to put together to look at the modal oscillation within the laser. So let's look at the first idea. In the frequency space that's in new, there are these modes which are possible. They are equispaced. Of course, because of frequency pulling, the spacing between them may not be C by 2L, but more or less for simplicity, let's consider as C by 2L. I'm calling this delta nu as the separation between the modes C by 2L. And there is also a width of the gain profile, delta nu G, and variety of things are possible. So we have the following two possibilities. The first possibility is that my delta nu gain, that's a width of the gain medium, is smaller than the width of the bare frequencies, right? That would mean that if I plot my gain medium in this frequency space, right, then you see that my gain medium has got a width which essentially has, this is my delta nu G, which is certainly smaller than the spacing between the bare cavity modes. And hence you see almost trivially we would get single mode oscillation. Under the gain curve, the other modes which are removed from the gain curve, these modes are not going to oscillate, and we are going to get a single mode oscillation for this mode. But you see, there is a problem with this. What we are saying is that my delta nu is large, right? It immediately implies that my L is small. So you will see that by choosing L to be small, one is effectively decreasing the amount of active medium that you can contain within the mirrors, right? So invariably your power levels will be low. So one doesn't really decrease the size of the cavity to obtain single mode oscillation. One doesn't do that because it severely limits the amount of gain that one can draw. The most common situation is the other condition, which is that my delta nu G is larger than delta nu. And typically, for example, if I'm looking at something like a helium neon laser or a ruby laser, so you see that my gain curve usually will be much broader than delta nu, which is the cavity frequencies. And now you see, one is trying to look at systems where this condition is actually satisfied. This is where the problem comes. So let us now put a few more ideas together. You recall that we have a condition called the gain threshold. The gain threshold essentially corresponds to a level which captures the loss in the system, plotting gains on the y-axis. My x-axis is frequencies, and you see that this is my level of the gain threshold. Right now, you see clearly if this is the level of the gain threshold, you will see that a specific set of frequencies will now tend to oscillate right within the gain cavity. Why? Because you see that the frequencies that I'm marking 1, 2, 3, 4, and probably 5. These 5 frequencies have gain which is equal to, the gain here is equal to or larger than the gain threshold. So these frequencies are going to oscillate within the cavity. Whereas frequencies which are such that the gain is lower than the gain threshold, for example, this frequency to the left and this frequency, and all such frequencies which are away, which are below the gain threshold, are not going to oscillate, right? So clearly now you have multiple frequencies trying to oscillate under the gain curve. Now this is where we need to worry about whether the gain medium is homogeneously broadened or inhomogeneously broadened. So we will first look at homogeneously broadened gain medium, and as you can see clearly, as these modes start oscillating, the amount of field within the cavity increases. So when I am seeking a CW oscillation, then in that case, we see that the gain clamping condition happens. That is, my G of nu becomes equal to G threshold. What that means is that if this is my threshold value, then you see clearly the same gain curve which I had plotted on the top is now going to get saturated, and you see that you would get a gain curve which is of this kind, and this has got a tremendous physical consequence. The consequence is that only one mode, which is the mode which has the highest small signal gain, if you like, is the one that would oscillate, because every other mode now, right, all of these other modes which are beside that uh, central mode have got a gain which is lower than the gain threshold, right? This was my level of the gain threshold, and what we have is that the original gain curve has now got saturated as the intensity builds up, right? We require that the gain is equal to gain threshold. That is what is the condition for CW oscillation, continuous wave constant output, and hence only a single mode oscillation occurs. Now, let me be very careful about this. So for example, you would find that a ruby laser actually shows multimode oscillation. That is because of the fact that even though it is a homogeneously broadened laser, and if I do not take care of eliminating the effects of spatial hole burning, because spatial hole burning leads to now collection of chromium atoms which are individually being saturated to different levels depending on their spatial location, whether they are at the node or at the antinode, right? So because of that, you see that multiple atoms get saturated differently is what leads to the multimode oscillation. But let us say you ensure that there is no inhomogeneous broadening mechanism, and if the system is purely homogeneously broadened, in that situation, the CW output invariably happens to be of a single mode. Only a single mode oscillation is possible if the medium is purely homogeneously broadened. On the other hand, if I now look at a system inhomogeneously broadened, that is, if I have an inhomogeneously broadened mechanism, I have the gain threshold condition, which is the same, and you have a medium that is inhomogeneously broadened. In that case, and this is where the competition between multiple modes will happen, because the field at, for example, this location might saturate locally, you see this transition, and this particular spectral packet of atoms is not going to affect the nearby states, right? So you see that you might have different light fields being saturated to different levels, and you see that invariably you will see that multi-mode oscillation is possible. There is mode hopping. Sometimes one of the modes gets saturated significantly, that it comes down, for example, like this, it comes down below the gain threshold, so this mode shuts off, whereas all these other modes continue to oscillate, right? And so on and so forth. One has to adopt some technique of choosing a single mode oscillation in an inhomogeneously broadened system. So in inhomogeneous broadening mechanism, right, inhomogeneously broadened active media invariably leads to multimode oscillation, and it becomes a challenge to actually obtain a single mode oscillation in such systems. So one of the ways to obtain is it's a very simple and powerful technique using something called a Fabry-Perot echelon, and it is based on a simple idea. I will not get into too much detail of this, but you can clearly see that the mode separation delta nu is given by C by 2L, and if I make L small, you see that mode separation is going to become large. So what I do is the following. I have a cavity, right, which has got my active medium, and the light, for example, is bouncing back and forth, and this is my laser output. So what one is doing here is introducing this Fabry-Perot echelon, which is basically it's a cavity which is extremely small. So what you have is, a cavity that is extremely small, and the light, so the light that is supported by this combined cavity, right? This has got a length capital L, and this has got a very small distance between the two faces within the Fabry-Perot echelon. Let me call the distance d. So you see that for a mode to be oscillating in this combined cavity, it needs to be a mode of both the systems. So let me just show that graphically. So for example, we have the original mode as this, and you also have the modes which are associated with the Fabry-Perot, which might be far separated, right? Because these modes are separated by, C by, let's say, 2D, where D is a separation between those, and this separation of the modes C by 2L. So and you see that now if I have a gain medium in such a system, so you see that there is going to be, one has to align such a way that one of the modes of the combined system actually overlaps with the mode of the Fabry-Perot, and only this mode is going to oscillate, because all these other modes, okay, are not going to be allowed within this cavity, right, within this Fabry-Perot. Simply speaking, what is going to happen is that these other modes are going to get reflected off and not going to be allowed within the Fabry-Perot, and hence one is able to now select a single mode for such a laser, right? So this is an way of selecting a, a mode. By the way, Fabry-Perot Echelon is a extremely simple yet a powerful device used in spectroscopy very widely, and I will not get into that too much. The other issue which I want to touch upon in this lecture is this notion of the Brewster window. That is, we want to now not only get a single mode oscillation, but we want to also obtain a polarized output from the laser. Now remember that the way lasing starts is essentially relies on spontaneous emission, where the spontaneously emitted photon is emitted within the lasing mode. Now, of course, there is no control over the polarization of the spontaneously emitted photon because it's spontaneously emitted, and variety of these spontaneously emitted photons contribute to the eventual buildup of intensity, which builds up at different polarizations which are possible, right? In order to now select a particular polarization to oscillate, one needs to create excess loss for the polarization that you don't want, thereby select a particular polarization that experiences gain in comparison to loss. The idea is the following. We use something called the Brewster effect, which you might have learned in school. So what you have here is, imagine that there is an interface where I'm going from a refractive index region N1 to N2, and I'm coming in with a input light. That's my input ray, and you get then I can write down by the Snell's law, you get the reflected light, and also you get the transmitted light, right? So this is my input, this is my reflected light, and this is my transmitted light. Now the situation is the following. The Snell's law simply governs the relationship between, the angles of incidence, right? Angle of reflection and the angle of transmission. So what you have is N1 sine theta is N2 sine alpha. This really doesn't talk about the polarization content of the field. So if you analyze the Fresnel coefficients which govern the polarization or the electric field vector associated with the electromagnetic wave, you will see the following. The plane formed by the input ray and the normal, right? This is my normal to the interface, right? So the plane formed by the input ray and the normal, this, as you know, is called the plane of incidence. So I can break down my input radiation into, two kinds of polarization. So one polarization is such that it is in the plane of incidence, and the second polarization is orthogonal to it, which is perpendicular. So I'm drawing these dots, which tells me that the polarization is perpendicular to the plane of incidence. So when I say dot, it means that the electric field vector is coming out perpendicular from the surface of this board. So there are these two polarizations which are input, and you see that different amounts of the light get reflected. So for example, the reflected uh, field might have different amounts of these in plane and out of plane polarizations. So we call the polarization which is contained within the plane of incidence as pi polarized, and the polarizations which are perpendicular to the interface are called sigma polarized, right? These are the two linear polarizations which are possible. And so you see that the amount of pi and sigma polarization content in the reflected and transmitted rays are different. Not just that, at Brewster angle, so Brewster angle, imagine that my theta was equal to theta Brewster, right? In that situation, what happens is that the same diagram is such that my reflected light and the transmitted light have an angle of 90 degrees between them. If this is true, then that is the condition for Brewster angle. What it means is that I can write down N1 sine theta Brewster equal to N2 sine alpha, but it so happens that alpha plus theta Brewster now, this is now theta Brewster, is equal to pi by 2, right? So I can write down my alpha as pi by 2 minus theta Brewster. So hence I can write this out as N1 sine theta Brewster equals to N2 cosine theta Brewster. I will just put my alpha back into this equation. All right. So what we get is basically the following, that my tan theta Brewster is the condition which is basically N2 by N1, which is what gives me the condition for the Brewster angle. So what is so special about the Brewster angle? So at Brewster angle, you see that in the reflected beam, there are no pi polarized components, right? So the pi polarized components are purely getting transmitted, okay? And there is essentially the reflected light contains only the sigma component field, right? Sigma polarized field. Of course, there is sigma polarized in the transmitted as well, but you see that at the Brewster condition, the pi polarization is completely filtered out from the reflected light. Now, if you look at such a situation, you will see that there is an extreme imbalance between the two polarizations. There is no reflection experienced by the in-plane polarization at the Brewster condition. So how does one utilize this in a laser? So what one does is we have the cavity, we will put in the active media, but now the active media is such that it has got a cut in a particular direction, and this is the way my light beam is bouncing back and forth. This is my output, and what one has done is basically this window which allows the light to go into the active medium. This window is such that the light beam makes the angle theta Brewster with it, right? So once I fix these values of N1 and N2, which is the refractive index of the outside medium and the refractive index of the window of this gain cell, for example, right? In that case, you see that this angle which it makes is such that that makes the angle theta Brewster. So what we are going to see is that this particular polarization, which is perpendicular to the Brewster plane, which is the plane in which I have drawn this diagram, see that this polarization is going to be thrown out of the cavity, thereby building up the in-plane polarization within such a cavity, leading to an output which is now linearly polarized in that direction, right? So you see that by repeated passes, one is going to filter out and retain only the in-plane polarization of this Brewster cut windows, and that is how one obtains, for example, polarized light. And maybe you also want to include within the cavity the Fabry-Perot. You will get not only a single frequency, but also you would get a single polarization, and that would be truly a single mode oscillation from such a laser. So there is another aspect that I have not touched upon, which is basically looking at the threshold condition in a little detail. So the threshold condition I have not explored too much because of paucity of time. So all that I want to mention to you is that imagine at threshold, so I'm looking at this G naught by G threshold as my ratio, and I'm looking at the number of photons within the cavity, for example. So you see that at threshold, you will see that there is, I just mentioned to you the result, there is a dramatic growth in the number of photons at a threshold, right? So below threshold, it is largely a thermal radiation, and above threshold, of course, it's all lasing. But you see, at threshold, you're going to see this dramatic change in the number of photons. This dramatic change is not only in the number of photons, but also in the photon statistics, that one goes from thermal statistics to this Poissonian distribution uh, in the uh, in the statistics of photons that are coming out. So we will not deal with this too much, but essentially I have put together these ideas that relate to the CW output from a laser. So the next what I'm going to do is going to talk about the pulsed lasers. And we will look at particularly two main mechanisms of obtaining pulse lasers. One is something called the Q switching, where Q stands for the quality factor of the cavity, and the other is mode locking. So I intend to discuss these time-dependent pulsed output from lasers in my next set of lectures.